Thanks for the intro. Wow, looks like a LAN party out there. Awesome. All right, quick note about myself. So yes, as was mentioned, I head the engineering for the Programmable SMS product line. I've actually been working with messaging, first started working with messaging back in 2000, which is a long time ago, I know. That's when the phones looked like this. And I've been with Twilio for a little bit more than 5 years. Seen a lot of changes during that time, obviously. We've seen some good volume growth, which has been a lot of fun. But I think what's a little bit more relevant for this presentation is some other changes that has occurred during that time. One of them is that we turned into a truly global communications company. So when I started, we had SMS delivery to 2 countries in the world. You can probably guess which. And not too long after, we expanded. Today, we deliver to 192 different countries in the world. And that means there are no off hours for us anymore. You know, there's always a peak somewhere in the world, and we can't really rely on any sort of off hours for doing anything risky or anything like that. Another change that has occurred, I mean, we've always had a lot of really interesting and diverse use cases using the Twilio API. But in the last few years, we've added a few that are really very critical. I mean, basically, life and death, frankly. Emergency notifications, crisis counseling, use cases like this. And they obviously provide a lot of incentives for us to make this as rock solid as humanly possible. All right, so the stack I'm going to talk about today is the SMS Platform. Basically, this is where we sit in the ecosystem between the API tier and the carriers. So when you post a request to the Twilio API, it first comes through our API tier that does basic authentication and rate limiting. And then we kind of handle pretty much everything from there until it gets handed off to the carriers. So authorization, validation, routing, storage, queuing, and translation to the weird and wonderful protocols that the carriers uses. And then we also rely on a lot of other services within the Twilio ecosystem, such as billing, data platform, and identity. When we have an inbound message, it's not illustrated here, but that basically goes the reverse direction from the carrier to us, and we invoke to and all that good stuff. Now, this is obviously an extremely simplified diagram. This is actually, the full thing. So you don't need to take this entire diagram in. It's meant to just illustrate the complexity. Krister from the voice team is going to have a great talk tomorrow about how their architecture evolved over time. We've gone through a similar journey, and if you're interested in that stuff, you should check out his talk. We currently operate over 100 different services spread across several hundred instances. And so it's a reasonably large system. Let's talk a little bit about what finite availability actually means. And I think a good way of thinking of that is in terms of the downtime that you can have over a certain time unit. So over the course of a year, if you have 2 nines, you can actually have several days of downtime, very generous. If you are at 3 nines availability, you're not less than 9 hours of downtime. 4 nines, it's less than an hour. And finally, by the time you get to 5 nines, that's basically 5 minutes, 26 seconds per year. That's not a lot of time, and it has a lot of implications for how we design and operate our system. Now, downtime is downtime. What do I mean by that? Some companies differentiate between scheduled downtime and unscheduled, and we don't really make that distinction. As I already alluded to, it doesn't really work for us because we have global coverage. And there are a lot of assumptions built into scheduled downtime, and that whether they will be convenient or not. And the fact is, if you have worldwide coverage, you will inconvenience someone. This has actually always been part of the Twilio DNA. I double-checked this, but we've never done any scheduled outages in the Twilio history. And I won't lie, it makes a lot of these big re-architecture projects a lot harder. As luck would have it, we find this to be a fun intellectual exercise, or at least I do so. However, not all uptime is created equal, and Jeff Lawson alluded to this in his keynote this morning, that uptime alone is actually not meaningful. We also want to account for partial outages. So basically, if the system is up, but it's not some parts of it is not working correctly, then we're going to account for that. That's a pretty simple equation. We just take the percentage of the impact. In our world, that will typically be the percentage of impact, and we multiply it by the time period. So now that we defined our terms, let's do a little snapshot of how we're doing. So far in 2017, we are actually at 100% uptime. Again, the really interesting statistic there is the service availability, and we're actually at 5 nines. In fact, we're closer to 6 nines at this point, but that feels like tempting fate too much to even put that number up there. Now, here's a quote that you may have seen. It's getting sort of popular in the industry. Everything fails all the time. Werner Vogel's CTO, AWS Web Services. And I think it's a popular quote because we recognize that it's both a simple quote but profoundly true. And it's a good rule of thumb when you're trying to build large-scale, high-availability systems to always keep this in mind. So the basic challenge we have is we're trying to build a reliable system out of unreliable parts. And that means we need to plan for failure. And I'm going to talk a little bit about that. I'm going to be talking a little bit about how you need to build self-healing systems. And then you need to introduce faults so they can test that they actually heal themselves. You want to build supporting processes around this, so deployment strategies. And it really all rolls up to building an entire supporting culture around this, where you're focused on constant improvement. Let's talk about planning for failure first. So I think one of the central insights here is that the availability of a system as a whole is a product of all the critical subsystems. Okay, that was a little abstract. Let's see if we can make it a little bit more concrete. Let's imagine that we have a system that just sort of evolves over time. It has 50 different systems or nodes maybe, and they're all needed for the system to work correctly. You know, this is the kind of thing that can happen if you don't really plan for availability. I call this a distributed monolith. And if they're all running at 5 nines, which is pretty good, then actually the end result is that we wind up with 5 nines to the 50th power, or 0.5 nines, which is really 3.5 nines. Not at all what we were aiming for. Slightly less contrived example, maybe you have 5 critical systems, again running at 5 nines availability. You know, now we're getting somewhere, 4.5, but we're not quite where we want to be. I mean, really, where we do want to be is that any single node in the system can fail, and it won't impact the system as a whole. So for stateless services, this is fairly straightforward. We can route around the failure with retries, and obviously we need to follow all the best practices. Well, first of all, we need to make sure that we have a low enough timeout that we can actually retry in time. And we want to have all the best practices in terms of exponential backoff jitter, all that good stuff. And the fundamental assumption here is that we can retry, that the requests are idempotent and safe to replay. If we have critical state anywhere, then that must be replicated somewhere else, because wherever it sits, that node can die. And that means if you're talking about a traditional SQL database, for example, you're going to have to do some sort of promotion from a replica to a primary. And whenever we have any sort of repair process like that, it must be automated. And let me walk through an example to illustrate why that is. So this is sort of a timeline of an incident, we can imagine, where we have a fault occurs, gets detected within a minute, an alert gets sent out, and 10 to 15 minutes later, we have a human engaged hands on keyboard actually working on recovering the system. Let's say it takes about 15 minutes to identify the problem and another 15 to recover. I would say this is pretty darn good. If you're doing sort of traditional human-in-loop DevOps, this is kind of best of breed, at least if it's in the middle of the night. And it's not good enough, right? I mean, you add up the numbers, it's 35 to 40 minutes. So if this is a truly critical system, you're just blown out your SLA for a while, several years. Let's do this again, run through the same timeline, but with automated recovery in place. So, we're talking about a minute to detect a fault, another minute to kick off automatic recovery. Let's say it completes in a minute or two. Now we're coming in at 3 to 4 minutes total. So if you assume this is the kind of error that happens once a year or less, we're good. If it happens more often, recovery needs to be faster. So we sort of talked a lot about single points of failure, and they fail as a unit. It's kind of right there in the name. It's a single point of failure. Now, one thing to be aware of as you scale up is that having these fleets of stateless services is kind of the bread and butter of building a high availability system, because you can route around a single node failure and whatnot. But one thing to be cognizant of is that the entire fleet can fail too. And there are many ways this can happen. For example, bad configuration. If you roll that out, obviously that's going to affect all the nodes in that fleet. We can roll out a bad release. So we can have a performance regression, basically a non-functional bug that affects performance. And by the way, obviously, the node doesn't really need to be down. If it's just impacted, if you have a bad enough performance regression, then it's for all intents and purposes unavailable, because our request won't complete in time. We may have some sort of resource exhaustion. So this could be a special case of a performance regression, or it could be that we're just out of capacity. And finally, kind of the dirty little secret of stateless services is that they wind up pushing their storage somewhere else, to some sort of backing storage system. And if that is down, more often than not, the entire service fleet will be down. And external services can definitely fail as a unit. Let's talk a little bit about how we want to handle these sort of systemic failures. Now, best way of handling them is to ignore it. And that's obviously a lot easier said than done. Another term for this is to fail open instead of failing closed. Now, this is where, if you haven't done so already, you need to sit down with the product manager, product owner, whoever defines the semantics of your service, and figure out what is that service, what are the service semantics going to look like without having these services available, because you call them for a reason. I'll give an example here. For example, within messaging, if you cannot route the message, if the routing system is down would be down for any reason, then we just fall back to a default set of routes that we determine based on the geography of the from and to numbers. Best practice here is to use circuit breakers. So they work pretty much like a real-world circuit breaker. They fail open, and you stop invoking that service, because invoking the downstream service while it's down is just going to literally be a waste of time. And we also run the risk of knocking that service down when it comes back up, because it gets hit with a retry storm of requests. Finally, we can fail over to a fallback system. And I'm going to do a little illustration of what that looks like. And this is actually a real-world case study of a could-have-been incident we had a while back. So this is traffic going to, we have a primary provider for a route here in orange, and then we have the backup in green. And we had an outage. This is actually a network, a BGP misconfiguration on their end that basically made them unavailable. So we can see they're unavailable, they recover a little bit, then they go down again. And all along, the traffic just flows seamlessly over to the backup provider. And I don't know if you can even see the timeline here, but it's good hours. So right here, this would have taken us down to 4 nines. And the moral of the story is, of course, you always want to have 2 of everything. I do have the cloud right there in the title, so I want to scratch the surface a little bit about some special considerations for the cloud. One of them is, of course, we're just at a bigger scale than it could have been otherwise, and that kind of it affects everything we talked about so far. It's also important to be aware of the basic topology. So these examples are going to be based off AWS. It's kind of an open secret that Twilio is deployed in AWS. Personal note, I love that. I've deployed a lot of software in physical data centers over the years, and the last 5 years it's been pretty much all in the cloud. I would not want to go back to a non-virtualized world. But you do need to be aware of how that ecosystem works. So, for example, the basic building block of AWS is a region. It has several availability zones that are like miniature data centers within that region. That is a unit of fault isolation in terms of networking, for example. So you definitely want to make sure you deploy your services in all ACs, so that if there's a network outage in one AC, then you will be fine in the other ACs. Also gives you more than one for free. But one thing that a lot of people don't realize or forget is that the unit of failure for cloud services, such as DynamoDB, for example, is actually the entire region. And so when they go down, they can, in fact, go down for the entire region. Some workarounds here. Well, again, we can ignore the failure. Actually, a workaround that's not listed here is we can live with the risk, because they don't go down very often. We can fall back to different regions. So for example, I've just mentioned DynamoDB. We can fail over to DynamoDB in a different region, and that means we need to set up some sort of region-to-region replication, but definitely a viable approach. We can fall back to a different implementation again. And full disclosure, we actually got bit by this a few weeks ago. Those of you that are in AWS may remember that S3 had an outage. Our core SMS product was fine, but MMS did in fact get bit by this because we serve media out of S3. So the way we're addressing that is we're actually building an alternate implementation that we fall back to if that's were to happen again. We can serve the media out of local EC2 file storage. So that's kind of covers some of the considerations of designing for availability. But this is really just one piece of the puzzle. We also need a whole set of supporting processes around this. And this is sort of stuff like automated test and validation, functional test, load testing, resiliency testing. We need a set of safe deployment strategies. We need instrumentation, obviously, with alerts and monitoring. And we need good DevOps practices. And what we found in Twilio is that it works really well for us to have teams operate their own services. I don't have time to cover all of that in detail, but I do want to dive into resiliency testing a little bit, because this lets us verify that our basic assumption is true. And our basic assumption is that we can lose any node in the system, and it won't impact the system as a whole. And so we want to test that assumption. So for example, wherever we have automated recovery within Twilio messaging, we actually test that several times per day in stage, and we kill nodes, and we verify that they recover correctly. So we can introduce faults like taking hosts down, processes down. Also, introducing network issues is super useful, both network partitions and degraded networking in general. And degraded networking turns out to be more interesting in some cases than clean network partitions. This is a huge topic. Bruce Wong is actually going to have a talk about chaos engineering right after this in this very same room. So I highly encourage you to check that talk out. He's going to talk a lot about the tools. I'm going to throw one tool out there that we use, and it's one of my favorites, both because it's a very useful tool, and frankly, I love the name and that he was able to get away with calling it Comcast. All right, so after we tested, we want to deploy. And I talked earlier about how deployment is actually it's actually a risky thing to do, because we can introduce one of these regressions that's going to take all the sources down. But also, Jeff Lawson talked this morning about how we really want to deploy as often as possible. We want to be agile, and it actually does also reduce risk because we're deploying very small changes. And this is also another case of, similar to what I talked about in the previous slide, we want to take something that's risky and we want to make it mundane by doing it very often. And we want to put supporting structures around it. So we have a set of steps we follow when we deploy software. And the first step will typically be shadowing. This is where we actually send production traffic both to a live node, but we also tee it out. It's like Unix T, where you can also send that production traffic to an instance, a dark instance, that's just taking that traffic and running in dry run mode, as we call it. So it'll do everything that that real service will do except affect state. So when it gets, for example, to the point right before it's going to send out a message, it will actually interrupt. So we don't wind up sending 2 messages to everyone. This is a great tool because it allows us to find a lot of functional regressions, but also non-functional. And by the way, the results do get compared so we can see easily if there are any discrepancies. We built this tool a few years ago. We actually showed it at Signal years ago, back when it was TwilioCon. Open source, you can get it off GitHub. After we have shadowed the instance, we proceed with a Canary. And this is a concept that you probably heard about before, or may have heard about before. It's basically analogies to the canaries that coal miners would bring down into the coal mine. And unfortunately, I think as engineers, we sometimes take that analogy a little too far. And so, literally, if the canary doesn't keel over, you say, OK, good, let's go. And it's important to check that impulse, so to speak, and be a little bit more deliberate about it. So one thing we do is we really try to inspect that new canary and see if we have any regressions, both functional but also non-functional. So we look at the system metrics. This is an example of that. You can see in red we have the canary, and we see that, in fact, we have a lot more memory usage now with this new version, and that's obviously a problem. Now, automation has been kind of a recurring theme in this talk. And so when you look at this, I mean, it's great that we can have a human see this and interrupt the deploy. But what's even better is if we can do that automatically. So we built some tooling around this, where we do a student t-test on the relevant system metrics. If we get a score that indicates that we have something that's that we have a huge discrepancy between the Canary and the existing generation, then we can interrupt the deploy automatically. And by the way, in this particular case, the discrepancy is very obvious, but there will be other cases where it's not quite as obvious as this. All right, so those are the first two steps. Once we've gone through this successfully, we can do a gradual rollout. So basically replace the old instances with new. One thing we try to decouple is deploying the software versus enabling it. And this is another way of minimizing risk. So we can have software sit out there and it's wired off. Then we can turn it on for certain accounts for testing, both by internal accounts and also for A/B testing and gradual rollout. And then when we are satisfied that the system works as it should, we can turn it on for everyone using the feature flag. All right, DevOps. So as I mentioned, we want to have engineering teams own and operate their own services. And this is great because it creates a feedback loop. Basically, the people that get paged about an issue are empowered to fix that problem, which is great. And they're also incentivized to fix it, frankly, because they don't want to get interrupted, and they don't want to be woken up if you're doing 24/7 pages. And this is really the first step towards getting to where we really want to be, where any fault is automatically recovered without humans in the loop at all. So we're not perfect. I already told you about one mishap we had a few weeks ago. And we make sure that whenever we have had an incident, we have an honest and blameless postmortem. And I cannot overemphasize how important it is for the postmortem to be blameless. Because if it is blameless, that's when you can get to the true root cause. And if you can get to the root cause, then you can fix it, and you can make sure the problem doesn't reappear. So this is another example of a feedback loop. We have a regular operations review meeting once a week. And this is where we look at our metrics and see how the system is performing. And we do this regardless of whether it's performing well or not. And so this is another example of a feedback loop where even if things are not broken, we can keep improving our metrics. And so this is what I together wrap up as sort of the supporting culture around this. We really want to make sure we have a culture of continuous improvement, because agility really is a mindset. And resiliency is a mindset. Agility is a mindset too. All right, so let's summarize. Everything fails all of the time. And so you want to plan for failure, and you want to design for availability. You want to build self-healing systems, and then you want to introduce faults to test them. You want to build supporting processes, like deployment strategies, that makes it easy to have the system be highly available. And you want to build a supporting culture that's focused on constant improvement. And again, resiliency is a mindset, and we don't take this for granted. This is something that we're always trying to improve on. And so while I'm very happy that we're at finance, honestly, we just want to keep improving on this. It's challenging, but it's also rewarding, and it's a lot of fun. Thank you very much. I will be in the back after this for any questions you may have. And if you don't find me then, I'll also be around both today and tomorrow. Grab me if you have any questions whatsoever. Thank you.